He will be speaking about scaling of extreme events in self-organized critical systems.
Okay, so good afternoon, everyone. First of all, I'd like to thank the organizers for giving me this opportunity to present my work. So today I'll be talking about the scaling of extreme events in self-organized critical systems. Here is the outline of my talk. I'll start with a brief introduction, then I'll also introduce the quick introduction of the stochastic Manna model and the BTW model. Then the idea of generalized extreme value distributions. Finally, I'll show the results and conclude. So in the introduction, I'd like to start with the idea of complex systems that refers to a system composed of numerous interconnected components. And the interaction gives rise to the emergent behavior that is often difficult to predict from the properties of individual parts. And the dynamics may give rise to large fluctuations in a relevant variable, resulting in extreme events. And these events may have cascading effects, and therefore it is important to understand these events, the statistics of these events. And other instances where these events have been observed are the self-organized critical systems, where so the idea of self-organized critical systems was put forward by Bach, Tang, and Weisenfeld, where they asked this question that what if systems naturally evolve into a critical state without tuning? So they introduced the concept of SOC, the mechanism in which the dynamical systems self-tune to a critical point. This can be considered as, this is the sandpile model, a minimal lattice model where grains are added slowly, and then sites topple when the threshold is reached, and avalanche emerge with no characteristic size, resulting in the idea that these systems evolve into a scale invariant state and criticality emerges. And here are some of the important references related to this idea. Then the question that why study extreme events in SOC models? So, of course, there is an intrinsic, the systems have intrinsic criticality. Understanding the rare and impactful events, this will be helpful in crucial for risk assessment, and this provides window into the resilience and fragility of the complex systems. And then there are also, it bridges the fields, the statistical mechanics and the extreme value theory for understanding and predicting real world phenomena. So here is the quick idea about the generalized extreme value distribution. Here's the CDF of the maxima X. This is, say, the observable of interest, and its CDF is expressed by this expression here, where mu, beta, and z are the location, scale, and shape parameters, where this shape parameter z determines what type of distribution it is going to be. So for example, when z is equal to 0, this becomes a Gumbel distribution. For z greater than 0, it goes to a Frechet. All right. So here is the stochastic Manna model and the BTW model, where we start with a 2D square lattice, and there's a randomly chosen site. We add a grain to it, and if any site exceeds the threshold value, it topples with the following rules. Now, these rules, here I is the site that topples and j is its neighbor. This neighbor can be, in case of Manna model, this can be 2 randomly chosen sites from the 4 neighbors, left, right, top, bottom. In case of BTW, all 4 sites will get a grain. Okay. In the present study, the observable of interest is the avalanche size and the area, the avalanche area. So avalanche size is the total number of sites that have toppled, and area is the total number of distinct sites that have toppled. And we obtain the maxima from the data set by dividing the data set into the intervals of fixed length, and then we calculate the maxima from those intervals. So here are the results. So we observe that mean, so we plot here the mean, variance, and mode. And in the inset, we plot this probability distribution. We observe that these quantities, the statistical quantities, these scales with the system size, and we say these are alpha 1 alpha 2 and alpha 3. And here PM, as we can see, this is scales as alpha 4. So if we do the scaling of these variables and introduce this scaling function, we were able to show, one can show that all these values, these alpha i's are all same. And so the result that I showed earlier was only for the Manna model. But then these are the alpha values for each model. In case of the size, if the observable of interest is the size, then these are the alpha values. This alpha 1, 2, 3 are very close, whereas alpha 4 deviates, and similarly in case of area. And here are the results for the BTW model. Here I plot the probability distribution Px of the extreme avalanche size x1 and in the avalanche area x2. So here is the avalanche size and avalanche area, and these results are for the Manna model. Similar results are there for the BTW as well. So here we observe that, okay, this varies as x to the minus 1. And if we do the data collapse corresponding to the probability distribution, we get this nice data collapse corresponding to the area and the size. Sorry, the size and the area. And here is the CDF corresponding to the Manna model. And we observe that, okay, for mu is equal to 0.01, this is shown in the red line, and which is the Gumbel distribution. And this black dashed line shows the GEV value. And similarly for this, for the area, in case of the Manna model, the CDF appears to be like this, in which we observe that the red dashed line represents the fitted data with the Gumbel family, and the black represents the fitted GEV with these values, with these parameter values. Okay. And here are the GEV parameters that we observe, and we see that the Z value for the size is very small, and we claim that, okay, it belongs to the Gumbel family, and whereas for the area, Z is greater than 0 and hence belongs to the Frechet family. So yeah, here is the conclusion. We conclude that with finite system size, the avalanche activities in the Manna model and the BTW model follows a power law with an upper cutoff. The statistical characteristics, mean, variance, and mode follow the system size scaling. And with the help of finite size scaling with GEV theory, we obtain scaling functions through data collapse. And for extreme avalanche size, the data collapse fits the Gumbel distribution, whereas it is Frechet for the extreme avalanche area. Okay, thank you for your patience.
We can take a few questions.
No, just curious to know if this, the properties of these models, self-organized critical models, does it depend somehow on the coordination number? So you work with square lattice.
Yeah.
Suppose if you had worked with triangular lattice with coordination number 6 or some other model, would anything change, or it's really not all that sensitive?
No, specifically we have checked it for the square
But
lattice.
in literature, is it done for other cases with different coordination graphs, like honeycomb with 3 sides, 3 neighbors?
Yeah, there are studies on other lattices and on the evolving networks also, but then I'll have to see if these results hold good there as well.
Any more questions? So then let's thank the author, speaker.